Добрый день. Good morning, good day, or good evening, everyone. We will start a worldwide conference starting from Twilight, Japan. You could see quite dark there. And the topic is neuromorphic optical systems based on phase change materials. It's my pleasure to present the first speaker, Dr. Robert Jones. Is one of the most eminent person in the field of DFT and computer modeling. Sufficient to say that his paper on density functional theory in Review of Modern Physics, published in 1989, cited more than 3,000 times. Last 10, maybe 15 years, Robert has been working on phase change materials, and literally it's nearly impossible to find a paper without citation of his work. He was graduated from Western Australia University and got his PhD in Cambridge. Most part of his scientific career, Robert has spent in Forschungszentrum Julich in Germany, and just in the neighboring buildings you can find one of the most powerful supercomputer centers in Europe. So it's also nearly impossible to beat Robert in terms of computer power. Dear Robert, your turn, please.
Thank you very much for the invitation to this meeting, and greetings from my office in the Julich Research Center. The weather is not so good, but we're indoors. I'm going to talk today about phase change materials and some of the lessons that we've learned from doing simulations.
Evgeny Sergeyevich.
I've given my email address there, and I'd be glad to hear from people who have questions. Also, I shall be providing this talk to the organizers so they can distribute the view graphs if necessary. We're going to talk about phase change materials of a particular sort, but we know that almost all materials exist in different phases, solid, liquid, and gas, and condensed phases can be amorphous or crystalline. And so why should we be particularly interested in phase change materials of our type? If they're particularly interesting, if the time scale is short and the different phases have different properties that can be monitored. And the materials that we've been looking at for the last 15 years, phase change memories, that the idea is that we can replace some of the standard means of storage by non-volatile memory. We know that if you switch off a computer, the random access memory is generally lost when you switch it off. It would be nice to have something which was always there. We have examples there. USB sticks are well known. Optical discs like Blu-ray disc and the like, and PC RAM is on the way in. So these are, the goal is to try and get a different sort of memory, and phase change materials provides that opportunity. The work in this area generally is considered to begin with Stanford Ovchinsky in 1968. He wrote a physical review letter where he reported on reversible electrical switching phenomena in disordered structures. He was able to observe, by switching an electric field on and off, a rapid and reversible transition between resistive and conducting states in thin semiconductor films. The materials we look at, the current view is that we're inducing transitions by laser light between crystalline conducting and amorphous resistive states. This is usually pointed out in this way. We have here, as time goes on, a very sharp pulse which takes a small bit to a high temperature above the melting point. It cools down and is disordered. This is a rapid process, and it is not part of the problem. The problem is to crystallize the reverse direction, to make a crystal bit, a small piece, nano-sized, And this is done by a somewhat longer pulse, which is of less power, so that it does not keep the thing melted. We have here we obtain a crystalline material. The astonishing thing about the materials that we're looking at is that this process can take place in nanoseconds. This is very unusual. The melt quench stage is fast. The crystallization, depending on the material, can be between 5 and 100 nanoseconds. Of course, it would be nice to get this as low as we could, and we started off at about 100 nanoseconds with germanium telluride, and it is continuing to improve. And the question is, which materials should we use? And of course, there's an infinite number of alloys that you can make. And here we summarize more or less the experience of some decades of work of trying to optimize the materials that could work as the phase change materials I just showed. And it seems that we always come back to alloys of germanium, tellurium, and antimony. This is not to say that if we replace germanium by tin or antimony by bismuth, that we don't have a phase change materials. It just seems that experience has shown that this combination has properties that are better than other mixtures. There are two regions in this GTE-SB triangle that are very favorable. Firstly is on the line joining GETE and SB2TE3. These are alloys of this form here, starting at one end, going to the other, and something in between. In this region here, we have what people call group 1. These are the GST materials. And we have another region here, which is predominantly SB antimony, SB70, tellurium 30. In this region, there is also favorable behavior, and often with silver or indium, and we call this AIST. Now, as I said, these are not the only possibilities, but they seem to be the most favorable. This is summarizing the experience of maybe 2 decades of trial and error. The nucleation takes place in these materials, we have the crystal growth occurring. Here is the polycrystalline layer. Here is an amorphous material that the crystallization takes place through nucleation here inside. And it is also possible in other materials that the nucleation takes place beginning in the crystalline area and proceeding inwards. Important for us as simulators is that these materials, germanium, antimony, tellurium, are main group elements. The valence electrons causing the bonding are S and P-like, and I shall return to this point later. The work most of the work I shall be talking about here now is work which took place in Japan, Yamada and Matsunaga at Panasonic. I should also mention the group of Alex Kolobov and colleagues at AIST in Tsukuba, and Shinji Kohara will be talking in the next talk about some of the work which has been done at Spring 8 in the experimental side. And in a remarkable paper in 1996, Yamada made a suggestion. He says it is believed that the structure of these favorable materials, I'm looking at GS225, I've got the formula here, was of the form of rock salt structure, with one of the sublattices, one of the FCC sublattices being purely tellurium, and the other sublattice being a random mixture of germanium, antimony, and vacancies, because vacancies are crucial to the operation of these materials. This, I think, is basically a suggestion, but it was followed up, this is now 10 years later, by the same group, that they looked at a great range of these materials, this family of GST materials, this pseudo-binary system, and they said that in all cases where they could do X-ray diffraction, they would be able to find a structure which was a rock salt structure containing an enormous number of vacancies within its crystal. So they even came up with the number, if you have X here, defining the mixture between GeTe and Sb2Te3, we have a certain fraction of vacancies. If I look at this formula, it's important to note that tellurium atoms are at least 50% of the atoms here. They're in GeTe, they're 50%. Otherwise, more than half of the atoms are tellurium atoms. And it was pointed out by, in this paper by Matsunaga, and Yamada was involved, that this led to a closed p-shell bonding. Now the question is, we're confronted with, as a theorist, we're confronted with an awful lot of information, and how can we approach them? Well, I would say that the relationship between structure and function has been follows my path in condensed matter physics. I've been interested in many sorts of materials, and it was always to understand the relationship between structure and function. A quote that I like to use is from Francis Crick, coming from his days as a molecular biologist, and this is from his autobiography. If you want to study function, study structure. And I believe this will hold in neuromorphic materials as well. The simplest example I could think of, this is the diamond structure. The greens represent atoms of carbon. Here we have graphite, a layered structure. Here we have C60. The only difference between these three materials is the arrangement of the carbon atoms, and yet they have completely different properties. Now, how does a theorist, we have to be able to say, how can we calculate the structure? What is our role in this whole business? And in principle, it is simple to state. If we can calculate the total energy for an arrangement of atoms, diamond structure, for example, then repeat this calculation for all possible structures, we obtain a potential energy surface. The minima give us the stable isomers, and the energy variation will give us the heats and paths of reactions. So, in principle, of course, we should discuss the free energy, because we're looking at something which is going on at finite temperatures and all sorts of other contributions to the free energy. But the potential energy surface is essential input to all calculations of this nature, and it is the focus of most of the work done by us and others. And there are two distinct problems. Firstly, how do you calculate the energy given a set of arrangements, an arrangement of atoms? Traditionally, in small molecules or in atoms, we can do this by calculating the wave function. And if we know all the interactions in the system, we can calculate the energy. The problem is that the numerical difficulty grows very rapidly indeed with the increasing number of electrons. So that this, in a system where I'm looking at many atoms, this is really not on. A second problem is that the number of possible structures, isomers if you wish, grows extremely rapidly, in some systems exponentially, with increasing number of atoms. If we take a particular molecule or cluster, we might find a local minimum in the energy surface here, but we have to find a way of ruling out other candidates, other structures, or finding these ones, determining which are the most probable. This is an incredibly difficult problem, and it is, in fact, I think, even more difficult to solve than calculating the total energy. The energy calculations I'll talk about use the density functional theory. They are very useful for many systems and are the basis of our energy calculations throughout. I should point out that this is an approximate method, and I view it in the sense of the argument that Dirac used. In 1929, he saw immediately after the Schrödinger equation that in principle, all you needed to do was to calculate the wave function and you could calculate the energy. But in fact, this is an impossible task. He saw this in 1929. And what we need, the exact application of these laws leads us to equations which are much too complicated to be soluble. So he said, we need approximate practical methods to replace the exact solution. And I view density functional theory as such a method. I've been involved in density functional theory, as I was introduced, a long time, and 2 review articles I've written. As I said, I will hand my I'll pass my talk on to the organizers so that all of the references can be obtained. The most recent and much more up-to-date one was in 2015. The density functional theory aims to calculate ground state properties of a system of electrons and ions in the field of the nuclei. And it says that they are functionals, they are determined by the electron density alone. In other words, if you know the electron density, you can, in principle, determine ground state properties. Now, we are interested, in this case, in the total energy. And this tells us that the total energy can be determined from a knowledge of the density alone. Now, the second point in Hohenberg and Kohn is that there is a variational principle on the relationship between energy and density, which is minimized by the ground state energy and density. I shall not go into these details, but I shall pass the equations on. A particularly clever way of splitting up the relationship between energy and density into equations that you could work with was made by Kohn and Sham in 1965. They separated off the total energy, not of the real system, the kinetic energy, not of the real system, but for a fictitious system without electron interactions. These terms here, this is our external field of the nuclei, and we have an interaction between the electrons. This is the Coulomb potential. And all of the other things they didn't know, they threw into a numerically smaller but complicated term called the exchange correlation energy. This separation made possible the equations the Kohn-Sham equations applied not to the physical system with interactions, but we could determine the exact energy for the physical interacting system that we are actually interested in by solving equations for an artificial system where there are no electron interactions. This is a great simplification. It comes at the price of having to make an approximation in this term, and a huge amount of effort has gone in over the last 30 years at least in determining the best possible approximation. The approximation that was suggested by, what was used by many people and by us at the beginning, the local spin density approximation, where we obtain the relationship between this term and the up and down spins from calculations in a homogeneous spin polarized electron gas. It was even in the first paper by Cohn and Sham, they said, you do not expect an accurate description of chemical binding. But in some years later, people started to use it on molecules, clusters, and the like. And much later, indeed, in around 1991, 1992, the chemists saw this as the approximations then in use led to a breakthrough in chemistry. In fact, it was so dramatic that in 1998, only 7 years after this, but a long time after this first papers, over 30 years after the first papers, Walter Cohn was awarded the Nobel Prize, or half the Nobel Prize, for his development of the density functional theory. Today, the density functional theory is certainly the most widespread method of calculating electronic properties in extended systems. It is also probably now the most widespread method used in calculations of molecules and systems of interest to chemists. Now, that's one part of our problem. The second part of our problem is that we have structures. We simply don't know what the structure is likely to be. And we have to have a method for searching out on this energy surface and looking for stable or metastable structures. This was done by Carr and Parinello in 1985, where they mixed, if you wish, molecular dynamics, where you have a kinetic energy term, the system moves around looking to minimize its energy, but they calculated the forces and energies from density functional theory. There are different ways that these are implemented, and over the years, this has become a much better system. There have been many improvements in algorithms, and the hardware, of course, continues to increase in power at about a factor of 1,000 per decade. There are very many programs available. Some CPMD program is the one that we have used. CP2K, you can use this without any restriction. CP2K is also from the same house, if you wish. They use a mixed basis set. It is not as well parallelized or parallelizable as CPMD, but it is very efficient. Very used by very many groups is the VAST program from Vienna, which now can do many other things. I mean, I talked with Georg Kresse some time ago, and he said that they were not able, if you have a massively parallel machine, CPMD was the way to go, but I think that VASP has made a lot of progress in this area. The approach, this mixture of density functional theory with molecular dynamics, can be referred to in this way like I do. Some people refer to ab initio molecular dynamics or first principles molecular dynamics with FPM and so on. Now, if we're interested in the phase change materials, we can ask what's so special about these materials and why do they crop up all the time when you're looking at these optical phase change materials. Why is the structure a rock salt structure, and why should, out of something really quite messy and amorphous material, should you get a perfect tellurium sublattice? Well, the density functional perspective on these particular materials is a very favorable one. These are main group elements. They are bonded by S&P electrons. And over the years, I think I have looked at all of these elements as clusters, as solids, crystals, and the like. And so I am well aware that these materials can be described really quite reliably in their structural terms by the method of density functional theory. This is a big advantage. If you are interested in materials where you have transition elements with a partly filled D shell, or rare earth and actinide elements with a partially filled F shell, you often have to do work quite hard. The standard approximations that we make in standard functionals do not work in many cases if you have these materials, and so it is favorable to us that we can use standard methods. I will come back to that at the end. Work, when I say theoretical work, there was work done by theoretical work done accompanying the earlier work right through to the mid about 2005. When I say theorists became involved, I mean we are groups of non-experimentalists. In other words, we don't do any experiments, and we require our experimental contacts somewhere else. Our first paper in this area with Jaakko Akala appeared in 2007. It was almost at the same time as Caravati. This is a group around Parinello and Bernasconi. Also 2007, and Hegedus and Stephen Elliott in Cambridge, they were using the VAST program, and they were also focusing on this material, G2sp2te5. And as you can see, we were rather modest in those days, relatively short simulations, a quarter of a nanosecond here, if you add up everything, shorter here, and really quite small systems here, but this is where it all began. We have worked for, I would say, about 12 or 13 years on these materials, and our most recent paper was 2016 on the simulation side, and in that paper there are all the references to the other work. We were focusing again on G2sp2te5, which Yamada at Panasonic refers to as the real paradigm of these materials. Our simulations with 460 atoms, and most simulations at 600 Kelvin, and some of these were extremely long. And this is a real problem point for the sort of simulations that we were doing then. But it is quite magical to watch the way, I have a video, which is, it requires just too much space to send around, but where I've watched it certainly 1,000 times, where this material, the disordered G2sp2te5, orange is tellurium and the others equal numbers of antimony and germanium. We have this material and we watch this over a simulation, and it changes almost magically into a structure where you have, in fact, something we're very close to what Yamada suggested, an almost perfect lattice of tellurium atoms, these are the orange, and growing order of the others. You see here, and something which looks as though it's got cubic symmetry, and of course we have vacancies in it. It is very important to notice that the crystallization process is not something where this structure falls into this one very quickly. The crystallization on a nanosecond time scale is such that this material, we know what its vibrations frequencies are, we've calculated them. It means that a nanosecond process involves thousands of vibrations. In other words, this whole system is moving around and lowering its energy, and ultimately it comes in here, and it's very difficult to say it is one particular process that is telling us what's happening. The big problem with these calculations is that if you are interested in a simulation time scale, which is roughly what the materials have, the order of 5 to 10 nanoseconds, with a time step of 3 femtoseconds, we have to do 2 million or more density functional calculations for a large system with 460 atoms. We don't mention it in the paper, but these simulations took approximately 2 years. on one of the largest supercomputers in Europe with 4,000 cores, 4,000 processors. So this is perhaps very nice to look at the result. The question is, this can't be, if we're interested in another system, do we have to spend another 2 years to understand what's going on? So we must look at alternative strategies, ways of doing molecular dynamics, which will enable us to look at the crystallization process, but use some sort of force field, a classical force field, for example, which can treat very large numbers of atoms and very long timescales. This, people view density functional calculations as giving reliable structures. Maybe we can use this information to get a good force field which we can use in classical calculations. Very early work was done here with on selenium, and the force field that came out is still used. It's not as good, I would say, as many of the more modern ones. But there are other methods now. Of course, the field has gone on, and data mining, machine learning, and so on. One way of approaching this problem is to use neural network methods or machine learning methods. Here's another one, to work out, to look at a small number, a relatively small number of density functional results, small number, it can be 30,000 of them, and use this information in a much bigger system. And of course, this has been done successfully by the group of Marco Bernasconi. And this, I think, is particularly interesting, is that you do machine learning, you watch the simulation go, and you get a, you have the opportunity to improve on this. If you get, you have a force field that is getting better all the time that you are doing these calculations. This is certainly a way to go. I should mention that just yesterday I received a paper where someone had used machine learning methods to look at something as complicated as platinum and to obtain really quite interesting mechanical properties of this material using machine learning. Well, let's come back to GESBTE and why are they special? Is it related to the structure that proposed by Yamada? Is it perhaps that the mechanism of bonding in these materials differs from others? Well, I wrote an article published 2 years ago on bonding in general, and I refer you to this paper. It is unfortunate that a referee insisted on the title being changed to bonding in phase change materials, which is the application I used, because this is an attempt to view the chemical bond and its history from the viewpoint of condensed matter physicists. And what I should like to do now is to give you a way of thinking about this problem, and a way of thinking that makes the model, I shall tell you, plausible without giving everything in the details. It has components that I would say are individually simple, but things are simple only if you're familiar with them. And I've discovered that the familiarity of different people, some things they understand very clearly and other points they're unfamiliar with. So there are some components in there. The first one is the nearly free electron model. I said these are sp bonded materials, germanium, antimony, and so on. And the nearly free electron model goes back to the 1929-30, where Bloch wrote the wave functions in a periodic system in terms of famous Bloch functions. And the important feature here was the wave vector of these wave functions, and the wave vector he used as a means of describing the states. Piles, just a year later, introduced for a weak periodic potential. If you have no scattering potential at all, these materials, the energy is simply a parabola, E equals k squared. And Piles pointed out that you would get, if we have weak potential, a gap at particular values of k. And these are Brillouin zone boundaries. Interesting enough, Brillouin came just in the same year, 1930. And this was a model which was a way of looking, if you have here electrons filled up to a level, open up a gap, and you can have an insulator or a semiconductor. Now, much later, over 20 years later, Piles introduced what has become known as the Piles distortion. Suppose we don't have something with a full band up to here, like a semiconductor or an insulator, but we have a band that is half filled. It is only filled up to here. Piles pointed out in 1955 in his book that this, if you have a metal, for example, and it's filled up to this point, you can gain energy by dimerizing the system. We have here, if you wish, a linear system, and we get each of these moves in such a way that we have a unit cell, which is now twice as large, the Brillouin zone boundary, half as large. What happens then? You could possibly get a structural change at this point, which is going to lower the symmetry. This is known these days as the Piles distortion. But in fact, it was known much earlier by Harry Jones, who was a author of the famous book of Mott and Jones in 1936. He pointed out that this mechanism, I repeat, 20 years before Piles, could be used to understand the structure of bismuth, antimony, and arsenic, which have bismuth has 6s squared, but they're all s squared p cubed. He showed that this simple argument, one-dimensional argument, could be applied in 3 dimensions if you, with a particular choice of zone, these zone boundaries where gaps can open up. This is what you get if you have 5 full bands and look at the Brillouin zone. This is much too complicated to look at. He found a simple zone where you could understand in terms of the nearly free electron what's going on in bismuth. Bismuth, terribly complicated, atomic number 83. He was able to explain then that bismuth was not a cubic material, but there was a distortion, a trigonal distortion into a rhombohedral structure. A second, very important for us too, is that bismuth, antimony, and arsenic are semimetals. They have conductivities which are really between an insulator and a metal, significantly different from both. Their electronic properties are different, but that could be understood, explained in terms of a simple model. These arguments in terms of free electrons can be applied also to systems. Here we have 10 electrons in the unit cell in bismuth, antimony, arsenic, but you can apply these arguments for 8, which is silicon, germanium, and this gives us a very simple way of making plausible the optical properties of silicon and germanium, for example. The second feature I want to point out is called secondary periodicity. And I've given, for this particular audience, I show you the first page of this paper in Russian by Biron in 1915. So it's more than 100 years old now. And Biron, remember that the periodic table of Mendeleev came in 1869, and this is 50 years later, that Biron simply noticed that a lot of chemical and physical properties did not change just regularly, smoothly as the atomic number increases, but there is a zigzag behavior. The heats of formation of oxides and chlorides, for example, that you can get pentachlorides of phosphorus and antimony, but not of nitrogen, arsenic, and so on. In other words, there was something going on that he called secondary periodicity. Now, you can see this if you look at the atomic orbitals of the elements involved. I've got here the main group elements, and we can look at then just how these are expectation values, if you wish, of this, how big this orbital is in one number. We'll see what the orbitals look like in a moment. And what do we see? We see something really quite dramatic. These are the S functions and the P functions. And we see that these orbitals, the outer valence orbitals of germanium and antimony, S orbitals, and P orbitals, are almost the same extent, although germanium has atomic number 32 and antimony 51. In other words, a much heavier element, and yet we have very similar valence properties. And in fact, the valence orbitals of germanium, antimony, and tellurium are very similar. They have different numbers of these orbitals, but you look at of these occupancies, and we have here, I've plotted them out, the atomic orbitals, and we see that these are very similar, S functions and P functions. Now, I ask you, this in the principle of trying to a model which helps you think about them, not to solve all the problems, but to think about particular. If we assume that these orbitals are they are close, but they are in fact the same, this would be a criterion, this goes back to the early days of quantum chemistry, that the strength of a bond depends on the overlap between the orbitals. It's called maximum overlapping. It goes back to Slater in 1930. If you include the vacancy sites, then and assume that the number of vacancies is that the average configuration is S squared P cubed. Now, this is something which was noticed by Matsunaga and co-workers and Yamada and so, that this was approximately true in the materials they looked at. If this is true, if we have orbitals that are the same in these cases, apply the argument of Jones, 1934, you can see that the cubic structure, a simple cubic structure, which can be described as two face-centered cubics on top of each other, is unstable, and you will get a trigonal distortion, and you will get, in the case of bismuth, rhombohedral, and in the case where you have something with differences inside, you have rock salt structure. Now, this is the second part of the problem. In other words, we've looked at something and it said, we see that these materials are very similar in terms of their atomic orbitals. If you look at the orbitals for other materials in the same families, you see this is not the case. The fit is not quite so good. The bonding will not be so strong enough. So we have here a simple explanation basically on the number of orbitals that you have, the occupancies, that you have a structure which you can obtain is likely to be, will be trigonal distortion and can be a rock salt structure. I said that these materials have the same orbitals, but they have different valence configurations. But if you have, you would favor this occupancy, S squared P cubed, we have, if the germanium and antimony, particularly the germanium, move away from the vacancies and tellurium attracts vacancies. This means locally on each site, we will have something which is approximating or closer to S squared P cubed. Now, I go to the second last slide here. And we see, if we look at this structure in detail and we compare with experiment where it's available, we do see that vacancies tend to collect around the tellurium atoms, that you get and germanium moves away from vacancies. And remembering that more than half of the atoms here are tellurium, basically the lowest energy in this simple picture is obtained by a structure closely related to the one suggested by Yamada. I repeat, I am not saying that this explains everything. It gives us a way of thinking about these problems where we could maybe say silicon is not as good as germanium, or phosphorus is not as good as antimony, and understand why, without doing a calculation that takes 2 years. I have focused again on the structure and the relationship between structure and properties. And this will apply, I'm sure, to neuromorphic materials, that if you are interested in properties, you will need to know where the atoms are. The way this is done in our work is to calculate the energy surfaces using density functional theory. I repeat, is an approximate practical method. And the work of the density functional formalism has many fathers, if you wish, goes back to the 1920s, including Dirac. It is really nice that you can combine a reliable way of calculating total energies with molecular dynamics in a scheme which works well on massively parallel computers. And we can use that to probe the energy surface and locate the energy minimum. Now, the goal then in general is to understand known properties and predict unknown ones. Now, I wanted to say at the end what, if I'm interested in a different family of materials, neuromorphic materials, what suggestions can be made. Well, if you accept that the relationship between structure and properties that you need to determine energy surfaces, then you will not be able to avoid density functional calculations in the condensed matter world. It's the best bet. And the mixing with molecular dynamics means that you can get unexpected structures, which are always very exciting. But the applicability depends very much on the elements, the atoms involved. And in the case of the phase change materials that we've been looking at, it's really favorable for our techniques that we can avoid many of the problems. However, if you're interested in materials that include transition elements, rare earth elements, or if you're interested in details in the electronic structure like the spin orbit coupling, which is crucial for many materials, then it is possible to do these calculations, but it is much more complicated and much more difficult to mix the density functional calculation with molecular dynamics. This gives you a feel, I think, for what we can do, for what we can't do, that we must be prepared to look at more modern methods of looking at minimizing energies and things like that. And we are in, we can't compete with the new methods, the methods of machine learning, and these may be applicable in your case. Well, I thank you for listening, and I'll give you a picture here from the corner of a street in San Francisco, in California, which I took a photo of. This is the end of what I'm saying today. Thank you. Okay.
And now Pepper's talk is open for discussions and for questions. Go ahead, please.
Maybe just short question, if it's possible, for the beginning of discussion. You mentioned about, you discussed also the phase crystallization process from amorphous to crystal. What's typical time scaling for such process you may expect?
Yes, well, good question, yeah.
Yeah, as I said, in the phase change materials we're looking at, if you look at germanium telluride, which is I think the first that was looked at in the mid-80s, the crystallization time there is of the order of 100 nanoseconds. And this is simply too long to be useful for a phase change material if you're interested in memory applications. The goal is to get it down to 1 nanosecond or something like that. They're not there yet, but that would be the goal. 10 nanoseconds is fairly typical, and but 100 nanoseconds is simply too slow. So that's the time scale we're looking at. Down to nanosecond if you can. It's really an incredibly short time for such a structural change to take place. Yeah.
Okay, it means it's gigahertz repetition rate devices could be developed with such materials. Am I right?
Sorry,
gigahertz repetition rate devices could be developed with such repetition rate.
These materials are used, for example, in the DVD read-write material, where you can buy a disk which has 100 gigabytes on it. These things you can buy in the store already. These materials, phase change materials, are used for optical properties. The goal is, of course, to have them in memory in the computer, replacing RAM, if you could get it fast enough. I mean, but the optical read-write materials for optical storage, this is what these materials, they used, GST materials.
Okay, thank you very much.
Bob, I have a similar question. What are criteria to have a very fast crystallization rate from the point of view of structure? It's only rock salt structure, or you could imagine something else?
Well, there's all sorts of things going on here. We tried, if you take antimony, just pure antimony, or tellurium by themselves, an amorphous material, and just leave it on the desk, these will crystallize by themselves. In other words, quite spontaneously. Tellurium above about 0 degrees Celsius just turns into a crystal in a very short period of time, in a few minutes. So this means that that these materials, for one reason or another, they will crystallize by themselves. And so if you use these materials, antimony and tellurium, the idea must be to slow down this process, because otherwise you can't use this for optical storage. And so our picture of what's going on in the antimony tellurium alloys is that we're adding silver and indium, and this is preventing this sort of catastrophic collapse of our storage material into something which is crystalline. Stephen Elliott is one person who's been looking at the crystallization process. How can you speed this up? There is some very nice work being done by people in Aachen and elsewhere, where they've looked at what's going on in SB and adding a small amount of scandium, for example, SBT, and adding a small amount of scandium and finding better crystallization process. But this is the hope, the belief of the people in the theoretical world is that we can help people ultimately. You have to produce an experimental device that works and that is stable at archival temperatures over 30 years or something. It can't be too crystallized too readily. And one of the hopes, certainly of the people in Aachen, and I was impressed by this work, was that they would say a small amount, maybe 10, 20% of scandium can accelerate the crystallization process, but you would end up with something which was still stable enough over a long period. I mean, perhaps Shinji will talk about the ways of handling this. We have focused up till now on crystallization as it appears in the pure material, and not how it's accelerated by other ones. I can see why you should accelerate it. Our calculations, if they run for 2 years, to get to 8 nanoseconds, this is far too long. I mean, something that's happening, this is, you simply can't keep repeating that. The hope is that from individual calculations that you can do in great detail, that you can learn something to focus on simpler models that also work. We also found the following. For example, we took 3 samples that were identical, but we had, and we at the same temperature, and they were at 600 Kelvin, but we had a different distribution of velocities to bring it up to an average temperature of 600. And amazingly enough, these materials all crystallized, but they crystallized at different times. The same structure, but with a different heat bath, if you wish. They crystallized, but they didn't crystallize at the same time. It was perhaps not surprising. I mean, it's a stochastic process that you have to understand, and but it was very frustrating to watch the ones that were not crystallizing and waiting until something happened, and then it went fairly quickly. In other words, there's a lot of things going on there that it's very difficult to pin down.
I have another question related to machine learning. So now it's become very popular. If you compare, let's say, a standard, maybe not standard, but usual DFT calculations with machine learning, what you could say about it?
So with what?
Machine learning and
yes.
Normal DFT.
Yes. Well, the claim is, I think it's believable that you're using, for example, let's take the one that I know best is the work of a group of Marco Bernasconi, and that they did a very large number of calculations on small. This is for GETE, okay, just 2 elements. And they did small groups of atoms, and then they, for this geometry, then they stored this number. And then they keep doing other ones, and they think that they have enough information there to describe the force field that's going on in reality. Well, the problem here is that this is a one-off fitting of an energy surface. In other words, if you want to do GST and not GETE, then you have to get another graduate student, and he has to then go through and work out which other structures you need and so on. In fact, they published basically they needed 30,000 calculations, but the number I had from Marco Bernasconi was much higher, than 170,000 calculations, do a very large number of calculations, and this pins down the forces, and the calculations produce results that are very close to the sort of simulations that we do. And they can do these more rapidly and so on. The goal is then to pin down a force field in advance. Once you've got that force field, you then are in very good shape. I think that machine learning, this is basically a good way to go, and the machine learning techniques have got a lot better. And the claims of all of these groups is that they are reproducing results of density functional calculations of equal quality, only that the systems are larger and the timescales are longer. I mean, this is, I think this is a very promising thing to do, and I don't have any experience with it, and some of the, I was a bit cautious about when Marco Bernasconi said he needed a graduate student for another 3 years for every new system. This was, but they have got very important information about germanium telluride over several years with this force field, and the quality is, I would say, comparable to what we can do.
Okay. Thank you very much. Any more questions, please? Okay, I guess, thank you very much for very nice talk.